Have you ever actually stopped to wonder how ChatGPT truly understands the words you type, or how Netflix somehow magically knows exactly what you want to watch before you even click? Well, today's explainer is going to reveal what I like to call the translation arc. We are literally going to look under the hood to see how linear algebra acts as this massive, hidden translation mechanism between our messy, complex human reality and the super precise geometry of a computer. It is an absolutely fascinating mathematical blueprint, and we're going to unpack it step by step.
Okay, let's dive straight into this blueprint. Here's our roadmap for today. 1. Translating reality into numbers. 2. Measuring similarity. 3. Transformation engines. 4. Determinants and space collapse. 5. Finding hidden patterns. And finally, 6. Real-world AI in action.
All right, part 1, translating reality into numbers. So, before a machine learning model can do anything, whether it's generating a mind-blowing image or recommending your next favorite song, it has to do one absolutely crucial thing. It has to turn abstract human concepts into structured numbers. And this brings us to the fundamental alphabet of AI, the vector. Mathematically speaking, it's just an ordered list of numbers that represents a specific data point in a geometric space. In machine learning, every single element in that list is a feature. The order matters immensely too. Think of it like a set of GPS coordinates that completely describes an object based on its traits, letting a computer plot it in high-dimensional space. To put that into perspective, let's ground this abstract math with some real-world stuff. It's crazy how seamlessly reality gets translated into geometry. To an AI, a student isn't a complex person with hopes and dreams. They're strictly a vector list: GPA, study hours, and attendance. A house? That's just a two-dimensional coordinate of size and price. Even wildly complex things, like entire paragraphs of text or high-resolution photos, are mathematically mapped out into vectors as word embeddings or pixel intensities. Literally, every piece of data in machine learning has to become a vector first.
Which brings us to part 2, measuring similarity. Now you might be wondering, once all our human data is mapped out into this huge multidimensional geometry, how on earth does the AI know if two things are actually similar? The mathematical fix for that is a beautifully simple vector operation called the dot product. To pull this off, you just take two vectors, multiply their corresponding values together, and add those numbers up. It's a lightning-fast calculation, and it acts as a direct measure of geometric alignment between two totally different things.
And this brilliantly illustrates exactly what the AI is thinking. If you get a positive dot product, those vectors are pointing in a very similar direction. They're highly aligned, so the AI says, yep, these two data points are similar. But if you get a 0, that means the vectors are completely perpendicular. Geometrically, they share 0 alignment, which tells the system that those features are completely independent and totally unrelated.
Moving right along to part 3, transformation engines.
Okay, so now that we have our data points and we know how to measure their similarities, we're leveling up. If vectors are the nouns in our AI system, the actual data, then matrices are the verbs. A matrix performs what we mathematically call a linear transformation. This is basically a rule that grabs input vectors and spits out brand new output vectors, actively manipulating the space while making sure grid lines stay parallel and evenly spaced. Matrices are the actual computational engines doing this work. So whenever you hear tech folks talking about neural networks calculating weights, what's literally happening is a giant matrix is applying a massive linear transformation to warp and shift the data space.
Let's picture what a matrix is physically doing here. It can scale a space, stretching or shrinking it. It can cause a rotation, spinning vectors right around the origin. It can reflect them, instantly flipping vectors across an axis like a mirror. Or it can shear the space, grabbing it and completely slanting the shape sideways. These fundamental geometric shifts are exactly how machine learning models process and manipulate information, layer by layer.
Next up, part 4, determinants and space collapse.
Now, warping all this space comes with some serious risks. We need a way to track the integrity of our data, and we do that using a critical tool called the determinant. It measures how much our space's area or volume is scaling. If the determinant is greater than 0, awesome. We've got a healthy transformation, space scales properly, and the data's orientation is perfectly preserved. But contrast that with a determinant of exactly 0. That is a mathematical disaster. A 0 determinant means the matrix is non-invertible, and the dimensions absolutely collapse. It's like taking a rich 3D box of information and squashing it totally flat under an anvil into a 2D plane. When space collapses like that, vital AI information is permanently lost.
Let's head into part 5, finding hidden patterns.
Assuming we haven't collapsed our space, we need a secret weapon to find the most stable, reliable directions hiding inside all these massive AI transformations. Enter the eigenvector. While a matrix transformation is busy rotating and shearing the space, making normal vectors totally change their direction, an eigenvector is special. It magically keeps its exact original direction. Literally, the only thing that happens to it is it stretches or shrinks in size. And the specific amount it stretches or shrinks, that's measured by its corresponding eigenvalue.
Now, what's really interesting about this is how these stable vectors unlock real-world magic. Because eigenvectors don't get knocked off course, they act as the truest underlying patterns of the data. AI uses them in image compression to find the most important facial patterns. Google originally used them in PageRank to figure out the true influence of web pages, and recommendation systems use them to discover huge, hidden preference groups, isolating clusters like hardcore sci-fi lovers or dedicated comedy fans from an absolute ocean of noisy data.
Which brings us to our final section, real-world AI in action.
All right, we've built the foundation. Let's bring it all together and see exactly how linear algebra dictates what you're going to watch tonight. Let's walk through the algorithm. Step 1. The AI represents your viewing history as a vector. Let's say you love action and sci-fi, but comedy isn't really your thing. Your user vector is 5, 4, 1. Step 2. The system maps its movie catalog. Movie A is a massive action sci-fi blockbuster, mapped geometrically at 4, 5, 1. Movie B is a rom-com, sitting at 1, 1, 5. Step 3. The AI acts. It fires up that dot product math we talked about to compute the similarity between you and those movies.
Let's run the numbers from movie A. The system multiplies your vector's values by movie A's values, adds them up, and boom, it drops this massive number, 41. That's your exact dot product score. Geometrically, a high score like 41 means your user vector and the movie's feature vector are pointing in practically the exact same direction. It's a huge mathematical alignment.
So the crucial point is right here. The AI calculates movie B and the score is only a 14. It instantly contrasts your massive 41 against this low 14, because 14 represents a really poor geometric alignment. The vectors are basically perpendicular. This is the exact moment the AI makes a decision. It instantly pushes movie A straight to the top of your personalized homepage.
And there you have it, the whole shebang. Linear algebra truly is the hidden blueprint of artificial intelligence. We've seen how vectors map reality, how dot products measure similarities, and how matrices perform linear transformations to uncover those hidden patterns. It is literally all about turning human behavior into high-dimensional geometry. So I'll leave you with this. The next time an AI flawlessly recommends a movie, a song, or a product, ask yourself, what does your geometry look like?